In today's video, I am going to discuss about the deduction of Hamilton's principle from D'Alembert's principle. This is a very important question. So we can start from D'Alembert's principle like this, that initially we all know that D'Alembert's principle can be stated like this: summation taken over fi minus pi dot del ri. Everything has its usual meaning. Obviously summation should be taken over I. Now just simply separate these two quantities. So the left hand side becomes summation taken over fi dot del I. Obviously summation has been chosen over I. On the right hand side you can see the part B can be modified as summation pi dot del I. Now here pi can be considered as momentum. Momentum is what? Mass into velocity. So mri dot. So technically pi dot can be rewritten as mi double dot. And obviously dot del I remains intact. Now as if we are trying to modify this expression like this, intentionally we are writing ri dot dot as ddt of mi remains fixed, dri dt, and dot del ri, keep this one intact. Now consider this particular portion as u, this particular portion as v. That means you are considering the derivative of u where v is fixed. Just imagine in this way, then it will be better for you. Now we know ddt of uv. Remember I told you this part to be u and this part to be v. So ddt of uv, it will have two parts. First part will be u into dv dt and second part will be what? U into dv dt. After that second part becomes du dt into v. Now you need du dt into v. So from the entire portion, if you subtract u into dv dt, that means mi dri dt dot ddt of del ri, this is del ri, then you will get this portion. So we have obtained equation number 2. So this part is u, this part is v. We are trying to calculate ddt of u into v, and for this purpose we have taken ddt of uv minus u into dv dt. So after getting equation number 2, again we need to modify this one. So how to modify this expression? Now we know this operator del, obviously variational operator, can be considered as a certain operator which can provide you a certain amount of small change in terms of ri. Obviously ri stands for displacement, which is not connected with time at all. I have written everything and all the important points has been highlighted. So you can see now we can consider this entire expression just like a differential operator. Also we know that this del operator, that is the variational operator, and the d operator can commute among themselves, so that we have this property that del of dx should be equal to d of del x. So forget about dx del x. Now simply let us consider dri dt, because we are focused about this quantity del ri. So del of dri dt can be made equal to ddt of del ri. So say this equation is A. Now with the help of this equation number A, again let us try to modify equation number 2. Now you can see the left hand side remains fixed, pi dot del ri, ddt of mi dri dt dot del ri. No need to change this one, but the next term has been modified. Initially it was mi dri dt. Here also you can find out mi dri dt, but after that ddt of del ri, as I told you, this is ddt of del ri. So ddt of del ri with the help of equation A can be rewritten as what? Del of dri dt. So that's why we have written this expression, or better to say we have modified or transformed this expression like this. So also for your convenience I have written from equation A. Now ddt of mi dri dt dot del ri, no need to change this one again. Now the second part can be written as what? Del of half of mi dri dt square. Obviously you can easily understand, if you find out the variation then 2 will be cancelled out, and that's why we can write this thing. So first part, keep this one intact, but what is the meaning of this dri dt? Obviously this is vi, so that's why we can write this second part as del of half of mi vi square. So this is the modified version of pi dot del ri. Now what is our objective? Obviously you can understand we have already obtained this expression. Why? Because we want to put everything in equation 1. So once you have obtained pi dot del ri, now you have to use this result in equation number 1. That is, on the left hand side summation fi dot del ri will be fixed, but in place of this you have to utilize this expression whatever you have obtained. Now here you can see, here we have obtained pi dot del ri, but on the right hand side here you have summation. So whenever you are putting this expression in equation 1, just put a summation over this entire expression and also put a summation over this expression. So you can see I have written the same thing as I told you earlier, summation pi dot del ri. So ddt of summation mi dri dt dot del ri minus del of summation taken over I half of mi vi square dot vi square, sorry, not dot, vi square. On the right hand side fi dot del ri, because this part is what, fi dot del ri, keep this one intact. Say this is equation B. Now we all know this part resembles to the kinetic energies expression, that is say T. So this is kinetic energy T of the entire system for all possible particles, and if the forces are conservative by nature, then we all know this can be rewritten in the form of minus del V. Now what is V? V is nothing but the potential energy of the system. So with the help of these modifications, again we can modify equation number B as ddt of this expression, no need to change this one, but second term will be what, minus del t. Take this on the right hand side, so it will be del t minus del v, so we can consider del of t minus v. Now let us integrate this equation, obviously this entire expression, with respect to the initial instant t1 to the final instant t2. Obviously t1 is the starting point of the motion and t2 will be the final time regarding motion. So that's why I have written initial time t1 to final time t2 of the motion. Now after integration you will get what? You can see here ddt is there. So after integration, simply this entire expression will occur from t equals to t1 to t equals to t2. You need to evaluate. On the right hand side, integration taken over t1 to t2, del of t minus v dt will appear. So this is equation number 3. Now again we can modify this expression. You can see del of t minus v of dt can be written as what? Del of t minus v, that means variation of this part, then dt, then t minus v del of dt. But del of dt is equal to d of del t. From where you can write this expression? Remember, del and d operator can commute, that's why we can write this. So del of dt is equal to d of del t. We know this part should be equal to 0, so forget about the second component, the first part will survive. So from equation number 3 we can write this entire expression is equal to what? Del is behaving like a fixed quantity, so del variation over t1 to t2 t minus v dt. Say this is equation number 4. Now in order to get the Hamilton's principle, we have to consider the motion of the system in such a way that the delta variation process, that means variational principle, will be such that all paths regarding the end points should be identical, should be fixed. There will be no variation at all at the extremities for any possible path. It can be fixed, it can be varied, whatever may be the character of the path, there will be no variation at the end points. So that's why you can say del ri at t is equals to t1 or even at t is equals to t2 will not give you any particular value, because there is no variation, it should be equal to 0. So technically you can say the left hand side of equation 4 must be equal to 0, so that you can see ultimately you have obtained from equation 4 del of t1 to t2 t minus v dt, this part is equal to 0. Now this is the well known Hamilton's principle, but in order to get the familiar form, you know t minus v can be replaced by what? Lagrangian, that is L. So simply let us put capital L is equals to t minus v, and if we put L in place of t minus v, then you will get the well known structure, that is del of L dt, integration taken over L dt. Obviously integration's lower limit will be t1, which is nothing but the initial instant, and final limit will be, or the upper limit will be t2, which is nothing but the final instant or final time. So in this way you can prove Hamilton's principle with the help of D'Alembert's principle. I hope you can find this proof very useful for your examination point of view, and obviously if you have any question or any doubt, you can provide it in the comment box. I'll try to solve it. Thank you.